So official. Okay. So do you see my screen?
Yeah, but not the lecture. You have to open your file before sharing.
I have already opened it.
No, you have to change to that window.
Yeah, change
where the file is open.
Where the file is open.
إذا بتروح تجيب شيء ثاني وستروح اللي كانت بختشي هكذا.
The arrow mark on the top, you have to click and then.
Do you see my screen now?
Yeah, empty screen.
Ah.
You have to open your file, and then.
Okay, so you see my screen, my talk now, not my slides?
No, we don't see.
No,
not yet. Oh, sorry.
Yeah, okay. I think the yeah, your screen is visible, not the talk.
Not the talk.
Not the talk. So I have donc here. Isn't try Emma?
No, I think that is okay. You don't have to change anything. You just go to the file. When you open the file, you will not be able to see us.
Yeah. I have opened already the file, but the problem is I on. So the file is here. It's already opened. In principle, you should.
Once again, maybe it is taking time to show.
Okay.
Yeah, somehow the screen is frozen now.
ترى بالليل أحلى يا أخي. لا مش في غادي. نسكر الفيديو لها. نسكر الفيديو لها. So نسكر الفيديو. ما نجمش نوري السلايدز.
تحب تعمل بريزونتي ماتنون شنو هو هذا اللوجيسيال؟
تيمز
يلزمو يعطيك لما
هي يعطيني لما دونك في بالي هوني
كيف فيك عرفتي لو بارطاج بارطاجي انت
بارطاجي
اي ما يخدمنوش بلاش اش عملت في البارطاج انا عرفتي لو بارطاج وغير لو بارطاج لازمك تعمل انزل اعمل لا
هذه عندها حق
انزل عليها
عندها حق زين
انزل عليها هاكا توجيه
yes it has come now.
Okay.
Yeah.
الانتجراليتي انت كملت الانتجراليتي حق قص هبط الفينيتر هيك بحال الفينيتر الاخرى حتى بالاخرى تمشي هيك الانتجراليتي
توا جيب اسمها من البلان اكرون لا عملها في شيء زين
باش نحل
لا ما تحلش كاميرا تحلش على البلان اكرون بل بلان اكرون لا مش غير
انا بس لا كيفاش تعملها
طلع فوق
هذا هو ايوا كيفاش
مش هيك سكرو تسكر قليل
ما فهمتش ايش عملت انا اش تحب
وكذا اريتي اوفري الباك دو بارتاج نحيتو به دونك هذا هو وتو نعملوا له افيشاج بلان ايكرون
هي ماوش باش نقول لك ما سيليكسيونيتش
عاد مش سيليكسيونيه دونك
اعمل اريتي
وين اريتي
انزل عليها
هنا
لا دقيقه ننزل عليها
ترميكا
حابة نسكرها كيفاش تسكرها باش تعاود تجيك الوحدة هذه متاع مش محلول عاود ترى هذه دقيقة هذا هو انت باش تعمل هذا لازم يقع السنة في شعر من ناحية ناحية ليش ما جيت؟ كان يدخل
ماما في سنتي
يا ما
برزنتاسيون به
تنزل عليه
إذا
لو شوفك شتى.
Is it okay now?
No, not yet.
No, okay, not yet.
No, you have to open your file and then share it.
Okay.
Yeah, but can you make it full screen?
Yeah. Plein écran. The problem is when I make it full screen, it disconnects. I don't understand what is the problem now. Donc, on vient partage. Non.
No, maybe we can continue with this. I think we should be able to read.
Yeah, this is fine. We can read.
Yeah, just go ahead with.
This is fine. Yeah.
This is fine.
Try clicking the arrows on the right hand side and left hand side instead of making it full screen. Yeah.
Yeah.
That is fine. Yes.
But this should be an.
كذا معنا هنا هذا عشان نكليكيوها مرة أخرى باليد يمين الأخرى خليها كأنه كانت حلو هذا من قبل انت كنت تعمل بيرو وتحل داخل حل داخل
ما هو ساعة جربني ما يخدمش
نكمل له بلان من هوني لا توزيع تكسر اعمل بلان من هوني Okay. Is it clear now?
Yeah, we can continue with this. I think this is good.
Yes. Yeah.
Unfortunately, it doesn't accept the full screen mode, which is nicer than that. But anyway, we can start. So first of all, thank you so much for this kind invitation. I deeply thank Professor Tangabilo for having sending me this invitation, and I'm very happy to give this lecture, which is not the first one I gave in Bangalore seminar, the APRG. And today I plan to speak about the LP Fourier Transform norm on some compact extension of locally compact groups. So let me start for some, let's say, preliminary things about the Fourier transform and about the LP Fourier transform norm on Rn. So we start with taking Rn as a Lie group, as a commutative connected Lie group with the standard inner product. And we identify the vector dual space Rn star with Rn through this duality, taking the inner product. And also we take the Lebesgue measure on Rn in a way that there is a normalization which takes the unit cube having the mass 1. So of course we define the Fourier transform, which takes any integrable function on Rn to the function f hat of xi for some xi in Rn, and so just to multiply the function f of y with this unitary character, I will say in some minutes what it replaces in the theory of general representation of Lie groups here. And of course, we have the classical Plancherel formula, which says that the L2 norm of the function of hat equals to the L2 norm of the function f for any function which belongs to L1 of Rn intersected by L2 of Rn. So this is some classical data. And now if you take any number p between 1 and 2, and you take the conjugate of p in a way such 1 over p plus 1 over q is 1. And now you take the function which belongs to L1 intersected by LP of Rn, then you have this inequality. So the q norm of the function f of the Fourier transform of the function f of f is dominated by this some constant EP here to the n, multiplied by the p function of the function f. Of course, here, this constant EP is the square root of this number, p to the 1 over p divided by q to the 1 over q. And if you take now the Gaussian f of x, which is equal to the exponential minus x squared over 2, then obviously we have that the function f hat coincides with the function itself, f hat, and then we get an equality here regarding this inequality here. So you have equality saying that the q norm of the function f hat actually is given by EP to the n multiplied by the p norm of this function f. Okay, so now if you like to generalize in some sense this theory to more general Lie groups, let's say separable locally compact unimodular groups of type 1. So type 1 means that any unitary representation generates a von Neumann algebra of type 1. So this condition is implied by the stronger condition of being CCR, which is said in French liminaire. And this has the property that each reducible representation pi, the image of CC of j, so the test function, all the C infinity function with compact support, so the image by pi, is contained in the set of compact operators. So in 1950s, Arishchandra proved that semi-simple Lie groups are CCR. And Dixmuir proved that nilpotent Lie groups are also CCR. But even in the simplest solvable Lie groups, EX plus B, the two-dimensional Lie groups, which is solvable non-exponential. So this is not actually CCR, but still type 1. And starting in dimension 5, there are solvable Lie groups which are not type 1. So let's stick to the stronger condition saying that the image of CC of j is sitting in the bounded operators. So we can fix also a hard measure on the group J, and using that we can take the LP of G, the space LP of G, so the space of LP of function of G for any P larger than 1, and then define the function or the operator value of Fourier transform pi of f, or f hat of pi, which is given by this formula, these Gaussian vectors for any integrable function and any unitary and irreducible representation of J. So we have the abstract Plancherel theorem, which says that there exists a unique Borel measure mu on G hat, satisfying this formula. So this says that the two norm of the function f with respect to this Haar measure and the group J. It is nothing but the integral against the Plancherel measure of the Hilbert-Schmidt norm of the operator pi of f for any function which belongs to L1 intersected by L2 of J. Of course, this entails that we can regard the Fourier transform f as a mapping from L1 of J to the space of mu measurable fields of bounded operators on G hat, defined by this formula. So you take any f in L1 of J and you associate it to the Fourier transform, pi of f, operator value Fourier transform. And you can define the Châtain class norm on all these fields of operator. So if you fix a field of new measurable fields of operator on G hat, you can define f of pi CR, so the Châtain class, being this trace, so this trace here. And then you take a norm on all these measurable fields. So you define FR to be this integral against the Plancherel measure, and you take all these things. And now you can regard the LR of G hat, the Banach space, defined by the measurable fields F such that FR is finite with this norm. So this is a Banach space, taking any function, any measurable fields satisfying that the norm is finite. So in 1958, Kunze showed the so-called Hausdorff Theorem for no-abelian group, which says the following. So given any p between 1 and 2 and q its conjugate, then you have the inequality. The q norm of the Fourier transform is dominated by the p norm of the function f for any f which belongs to L1 intersected by L2 of J. And this says that you defined a continuous operator, f of p, from LP of J to LQ of J. And we are today concerned with the norm of this mapping, this LP, the LP Fourier transform norm, which defined as an operator to be this quantity, so the supremum for all FP less than 1 to these quantities of the Q norm of the LP Fourier transform norm here, which is obviously dominated by 1 given Kunze theorem, so the so-called the Hausdorff theorem. So the outline of the talk today is the following. So I plan to discuss the LP Fourier transform norm for first nilpotent connected Lie groups. So in this case, we have generically a continuous spectral case, like the setting of Heisenberg group, for instance. I will talk about it later on. And secondly, the compact extension of nilpotent groups and some of their universal coverings. So in this case, the spectrum is a mixture of continuous and discrete parts. I will also explain what is the norm of the LP Fourier transform in this case. And the third part is the compact extension of locally compact group, which is new results. So since the last daily conference held in December 2015. So here we have obtained new results which generalize the point 1 and point 2. So let me give first some general results. So for instance, Rasso in 1974 showed that if G is a unimodular locally compact group, then the LP Fourier transform norm of the group, of the direct group R with G, is strictly smaller than 1 for any P between 1 and 2. And later on, Beckner in 75 showed that for Rn, for the commutative connected Lie group Rn, the LP Fourier transform norm of Rn is exactly EP2n. And in the first slides, I have already given the extremal function, which was the Gaussian. The Gaussian realizes the function for which we can obtain this equality in the equality giving the domination by the P norm of any function which belongs to L1 intersected by L2 with the Q norm of the Fourier transform function. And in 1977, Fourier showed that the LP Fourier transform of the group is 1 if and only if the group has an open compact subgroup. So it's not far from being compact. So this is this holds for any group having an open compact subgroup. And if you take now a compactly group with the normalized Hard-measure dj, and you take any function which belongs to L1 intersected by L2 of j, then if you have an irreducible root representation pi of j with degree dp realized on C to the dp, so we have this well-known Plancherel formula. So so you have this equality. Here we take the Hilbert norm here at this level. And the Hausdorff Theorem inequality for G says the following. So if you replace the Hilbert norm, the C2 norm, by this Chapman class norm, pi of f CQ to the Q, so see this is dominated by the LP norm of the function f for any function which belongs to L1 of G intersected by LP of G. And of course, this shows that the norm of fp of j is 1 because the function, the constant function f1 is a Maxwell function at this level. So the norm of the LP Fourier transform norm is equal to 1 for any compact Lie group. So let's move now for another category of Lie groups. So in 77, Russell showed also that whenever you take a connected, simply connected nilpotent Lie group, then the LP Fourier transform norm of the group J is dominated by the LP Fourier transform norm of its center, which is also something diffeomorphic to some M for some M. So this is a connected, simply connected vector space. Let's say subgroup of J. So it is something like R to the M for some M. And by Beckner result, this is actually given by EP to the dimension of Z of G. And this is the first estimate given for any connected and simply connected network group, but we will see later on that it is not the best. We can even make better. So in 1992, Jinko Onway, a Japanese mathematician, proved the following. So if you take the dimension of generic quadrant orbits of G star, you know that the Lie group acts on the Lie algebra J by a joint action, and then it acts on the vector space of the Lie algebra J, so G star, by the coadjoint action. So it produces the so-called the generic coadjoint orbit, like in the setting of Heisenberg group. And then any orbit has some dimension. So this is some smooth manifolds. And if you pick the dimension of generic coadjoint orbit, let's say the maximal dimension of all generic coadjoint orbit. So this is the Zariski open set in G star. Then Jinko showed that for any p between 1 and 2, the LP Fourier transform norm of the group J is somehow dominated by this constraint. So you take here 2 dimension of J minus M minus the generic dimension of all these coadjoint orbits divided by 2 here, which is better. So this is better than this estimate because this actually is is larger than this one. But Jinko assumed that the Lie algebra, the nilpotent Lie algebra, satisfies a strong condition, which is the fact that there exists an open dense set U of G star, such that the ideal generated by the union of all U in some Zariski open set in J star of all the stabilizer. This is the stabilizer of the action. I will come back later on. This is stabilizer of the action. I said that the Lie group acts on the dual vector space of the Lie algebra by coadjoint axes. So it produces orbits, and then it produces some stabilizer. And the G of L is actually the stabilizer of any L in this Zariski open set. So she assumed that the ideal generated by this union is abelian. And this is, of course, Heisenberg glue groups, for instance, satisfies this, but this is a bothering condition. It is a strong condition of the Lie algebra. And later on in 2003, we could, with John Ludwig and a student of mine, Kais Maui, relax this condition. So we showed that the estimate star holds for any connected, simply connected nilpotent Lie group. And let me remind, star is that. So star is that the LP Fourier transform is dominated by EP to this power, 2 dimension of G minus M over 2. So we showed that this estimate holds for any connected and simply connected nilpotent Lie group. But still, we are not quite sure whether this estimate is the best or not. So let's continue. First of all, I will give a flavor how to prove this result. So if you fix any nilpotent Lie group, so this is something like G is exponential G with G is the Lie algebra. So this is an n-dimensional real nilpotent Lie group of Lie algebra G. And you fix a strong Milsev basis of J. So something saying that the vector space spanned by the vector x1, xg is an ideal of G for any J. So this you have a flag of ideals which generate the Lie algebra. And when you jump from a step to another, you step by ideals. And you have this composed map from Rn to the Lie group, which takes any vectors, any elements x1, xn to this linear combination here. So this belongs to the Lie algebra, and you associate the exponential mapping, and you end up with something in the group J here. So this is the diffeomorphisms, and it maps the Lebesgue measure on Rn here to a hard measure on the group J. So this helps to define a hard measure on any connected and simply connected nilpotent Lie group. And of course, as I said, you have the coadjoint orbit here, so the action of J acting on any linear form here. And you have the stabilizer as I showed later. And an index G in one end is said to be a jump index on 4L if G of L plus GG is not equal to G of L plus G minus 1. So you can pick the collection of all jump indices for L. So you note it E of L. So this set actually contains exactly the dimension of GL indices, which is necessarily an even number. So this is exactly the dimension, and this dimension is an even number for any quadrant orbit of an nilpotent Lie group. Now we have 2 disjoint sets of indices S of t. So such that the unit is 1 of n, so n is the dimension of the Lie algebra, and you have G-invariant Zariski open set U, such that E of L is S for any LU, so it is common for all linear forms sitting in the G-invariant Zariski open set U. And you have 2 vector spaces, V and sub t and V sub s, which is nothing but the linear combination of x, r, I star. So this is the basis of the dual vector spaces of the Lie algebra. But you take here I in T and you take here I in S. So obviously G star is the direct sum of Vt and Vs, and Vt meets the set U through a section W, And this is actually a cross-section for quadrant orbit through points in U. So just in the case of Heisenberg, so this is something like R star. So this is the infinite dimensional representation corresponding to pi lambda, the Schrödinger representation for lambda not zero. So this actually general for nilpotent Lie group. So the direct sum of these two spaces corresponds to G star, and the intersection actually gives a cross section for quadrant orbit in let's say maximal dimension through points in U. So every G orbit in U related to representation pi meets this set W in a single unique element, and you can, by the way, define the Pfaffian file of the skew symmetric matrix. So MSRL, and in this way, you end up by defining the Plancherel measure for jihad for any connected and simply connected nilpotent group. So you just multiply the Lebesgue measure here by the absolute value of the Pfaffian, and the Plancherel formula writes that the two norm of any integrable function, which is in L2 of J, so this gives that it is equal to this C2, that this is the Hilbert-Schmidt norm at this level, and here this is the Plancherel formula for J8, and you have a nice, very nice cross section. It is something like semi-algebraic set in G star. And now, if you have this, you can therefore have the following description. So the Q norm now of any function which belongs to L1 by L2 of J, the Q norm is actually given by this formula. So just you look at the Chatten class CQ norm of the Hilbert-Schmidt here, and against also against the Plancherel measure. So the problem now is how to get a sharp estimate of this CQ norm of pi of f. This is actually a very important problem. So if you can get, let's say, a nice estimate or sharper estimate, you can get a nice estimate for the LP Fourier Transform of the Lie group. So for this, we can we used the Fourier-Rousseau theory or theorem proved in 1977. So the so-called the Hausdorff inequality for integral operator, which says the following. So if you fix any capital X sigma finite measure space, and if you have a Hilbert-Schmidt H, and you take K, a measurable B of H valued function on the direct product X times X, and you look at the capital K as an operator of L2 of X defined by this formula. So you look at some phi in L2 of X taking value in H, and so this is actually an operator which is an integral operator, and little k is here the kernel of this operator. Now, if you define this norm on little k, defined by this formula, taking all the time p between 1 and 2, and q the conjugate of p, and you define this norm. So you take here the Chatten norm of this operator. And we have then, so the theorem says that the Chatten norm of the operator k, so capital K, is dominated by this product, though this product of these two norms here, where k star, this is the involution of k, saying that k star xy is nothing but ky x bar. So this is very, very useful to get an estimate of the LP Fourier Transform norm of only groups. Now the second key point in proving theorem 1 is to look at the so-called localized version of the Plancherel formula. So this is very important actually. Maybe if I have some time to explain why is the reason to define this, because sometimes when you like to prove something on any connected nilpotent group, you are not capable to make use of an induction, for instance, on the dimension or on some homogeneous spaces. In this way, you use some localized Plancherel formula on the homogeneous space by taking some connected closed Lie groups sitting in the center. So you know, for connected nilpotent Lie groups, the center is all the time not trivial. So you can define some characters on Z of J. For instance, if you take any closed connected subgroup of ZJ, you take this character. So for psi in A star is the Lie algebra of A, and this is the dual vector space. And you can take J sub K hat. This is the set of all representation pi, unitary and reducible, such that the restriction of pi to I is a multiplication by this character. So obviously, this set is a closed set of G hat and homeomorphic to the orbit space G psi over J. So this is G psi star, which is nothing but this fine space, say sitting in G star. So this is a G-invariant space, and if you look at the orbit space, so actually this G sub K hat is homeomorphic to this orbit space. And now you can look at the LP space using some G-invariant Haar measure on G of G mod A, using the covariance relation by psi. So this defines the set of all measurable function f such that you have this covariance relation here at this level of all G in J and in A, and you assume that the P norm of LP of G is nothing but the norm over these homogeneous spaces. As I said, you fix some G invariant Haar measure on this homogeneous space. So the localized Plancherel formula reads as follows. So if you look at any function which belongs to L1 intersected by L2 of G mod A chi, so you have so you take this formula. So instead of taking the pi of f as earlier the integral over G, so you take the integral of a G of A, so something like f of J pi of J. So this is the unitary operator multiplied by this integrable function here. And you take this translation which belongs to this stratified unitary dual of J. So in this case, you have this formula. So the L2 norm of the function phi on G mod A is nothing but this integral. So just here you take the Hilbert norm also with some measure given by the measure, by the Delebesgue measure on the affine space psi plus the orthogonal of A.
I have a question.
Sorry, yes.
I have a question. So for this localized Plancherel formula,
yes.
Does it hold in general? Do you need A to be a abelian subgroup of the center, or can you take other subgroups?
All the subgroup of center are abelian here, because the center itself.
No, I'm asking, would it hold in general? Can I take another subgroup H? So that I have a.
It is complicated because the restriction, when the subgroup is not abelian, the restriction is not a multiplication by a character.
No, you will start from a representation of H.
Yes.
And then look at all the representations of G, which will have this as a component. That will not. That doesn't give you a Plancherel formula for L2 of G by H, is it?
Yes, yes. So if I understand correctly the question, you fix a subgroup and you fix a character on this subgroup, right? And then
it doesn't have to be a character. It could be a representation of H.
Sure. But I'm not quite sure if you can derive a nice localized Plancherel formula in this way. I'm not quite sure. Yeah.
Okay.
As a definition, it's okay, but the property of the Plancherel formula, I'm not quite sure if it is like this case.
Yeah. All right. Go ahead.
So the localized Plancherel formula says the following. So it is something similar, but so you have a stratified unitary dual, and this is very helpful when you like to make use of an induction over the Lie group J. So
sorry, one more
yes.
One more question. So is this equivalent to the decomposition of the G action on G by A, on L2 of G by A?
Yes, in some sense, yes, but you need some clarifications about measure and so on. Yes,
okay.
Yes. Because the point is when you look at the restriction of any irreducible representation to the center, this is an infinite dimensional, so the multiplicity is infinite. And when if you like the disintegration of the restriction, you have some multiplicity, and in this case, all the multiplicity are infinite.
Are infinite, okay.
Yeah, are infinite. So you need to make some clarification. But in another paper with John Ludwig, we described some decomposed operator and formula on these homogeneous spaces, even in the case of infinite dimensional multiplicity.
Okay. Got it. Yeah, thank you.
So now you have also this nicer formula. You have a decomposition of the Plancherel measure. So if you have a mu-measurable fields of bounded operator on G hat, you can decompose it on E star here first, and then you can use this stratified unitary dual, and you have this formula. So this is actually very helpful. And I'm not quite sure. Maybe it is okay for general, as the question in a row here. Maybe it is true for general subgroups, but we need to check. Yeah, but this formula is capital here in our theory because it allows to take some measurable fields from the whole group to stratify it into GK star with some characters. And now, if you look at the Q norm of the LP Fourier transform here, so this is actually given in the stratified version by this formula. So you integrate this over WB psi, and you take the CQ norm, so the Chatham class here, and you take the Plancherel formula here, and as I said. This stratified slide, so this slice, you take just the ZW, the semi-algebraic set in G star, and you make the intersection with this affine space. So the upshot is the following. So if you take any connected and simply connected, then put it in the group, and you take a central subgroup of J, and you take unitary characters of A, then for any P between 1 and 2, you have this formula. So the integral against the Plancherel measure of the Chatham class norm of PR of F is dominated by this constant. So EP is the same, but here you take the dimension of G mod A minus M psi over 2, and you multiply by the P norm of the function F. Here. And here, M psi is nothing that the maximal dimension of the quadrant orbits, but in this slide, not any L in G star, but just on G psi star. And when we make a proof of this theorem, it's easier to handle central subgroup. Because it makes to make available our induction hypothesis. So the induction is not easy in general, but when we intervene, when intervene these central subgroups and these characters, it makes it easier. And by the way, maybe I come back to the question of Naro. If you look at this formula, actually here. The first equation, So this is not available for any Lie subgroup, because when you take the Lie algebra of any Lie subgroup, you don't have subcharacters here. So the problem is here. So the utility of this formula is that whenever you take a character of A, of capital A, you have all the time subcharacters. So you make the induction. In the general Lie groups, you may take some linear form in the Lie subgroup, but it takes some infinite dimensional representation. So I'm not quite sure whether this formula have an analog if you switch to general Lie groups. But as I said, this is very useful when you take some subgroups in the center. Anyway, so of course this gives us the theorem with John Ludwig and the Case-Smawi, because after proving that, just you take A equal A, so the trivial subgroup, and you end up with the estimate we built. So the proof is run through an induction procedure on the dimension of G mod A plus dimension of J, and this makes use of Hausdorff inequality for integral given by Russell-Fourier as I explained. So some remarks. So this is the most general so far. So this estimate for connected and simply connected nilpotent group is the most general so far. We don't have any new result from this since this theorem. And Klein and Rousseau in 78 considered just the case when Q is an even integer, and so P is 2Qs divided by 2Q minus 1. So this is the situation where the conjugate of P is an even integer, and in this situation, in this particular situation, so they prove the sharper estimate. So the LP Fourier transform of any connected and simply connected nilpotent group is dominated by EP to the dimension of G, which is better than ours. But the problem is we cannot prove so far that this holds for any P, but only for some specific P. So related to the situation where Q is an even integer. And in this setting of the 2n+1 dimensional Heisenberg group, so we have an equality. So the LP Fourier transform of the Heisenberg group is EP to the dimension 2n+1 here, but still Q is an even integer. So in this case, the authors showed that there is no external functions. So they assume that there exists an external function in this setting, but they show at the end that it is 0, so it is not an external function. And this means that they take a sequence of inside the LP of J, which tends to the norm, but no external function. And the problem of finding the exact norm for general cases is still open, even in the case of Heisenberg group. So far, even in the case of Heisenberg group, we are not quite sure whether we can establish this theorem. So we believe in it, but we don't have any proof for that, even the three-dimensional case. Okay, now it is all the time possible to remove the assumption of simply connectedness. So having now a connected nilpotent group, we can remove the fact that it is simply connected. So let G tilde the universal covering group of J, and then so this says that G is given by the homogeneous space G tilde over gamma, and gamma is the discrete central subgroup of J. And you have an exponential mapping from the Lie algebra to the universal covering, and you have lambda, which is a discrete additive subgroup of G of the Lie algebra, and you have exponential lambda is gamma here. And you look at the Lie algebra of synthetic hull of lambda. You call it H tilde. So H tilde is a connected, simply connected Lie subgroup of G tilde, and so you have this. So H is nothing but the quotient of H tilde over gamma, which is included in J, and then this quotient is compact. So gamma is contained in H tilde compactly. So this is actually the compact maximal subgroup of J. So in this way, we proved with the Junko-in way that we can also give an estimate of the LP Fourier transform norm of nilpotent connected Lie group without the assumption that it is simply connected in this way. So if you fix such Lie group and you take the universal covering G tilde and you fix the maximal compact subgroup H of J, and as I said earlier, you fix also the maximal, the M, the maximal dimension of generic quadrant orbits of G tilde. Then for any P between 1 and 2, though the LP Fourier transform norm is dominated by EP to the dimension of G mod H here minus M of 2. In some sense, this said that the compact part does not play a big role in this story. I will explain it correctly later on when we look at the some compact excitation with compact subgroups. So this, for instance, another case where so the Euclidean motion group, so M of n. So this is the rotation group acting on Rn naturally. So SON semi-direct product with Rn. And you have, so any element is noted by EK, where E is vector in Rn and K is in SON. And this acts on Rn by isorotation. So we describe the multiplication as follows. So this is, I think, 1 hour. And we take a Haar measure M of n by the multiplication of the two Haar measures. And when you take a character on Rn head, described by this formula, and you take the n, the last vector in the canonical basis of Rn, then M of n acts naturally on Rn hat, and you have this action. So AK acting on chi, and you define on B. So this gives this formula, and you have a stabilizer. The stabilizer is nothing but described by this formula. So this is a K prime semi-direct product of Rn, and K prime is something isomorphic to SON minus 1. And now, if we fix sigma in K prime hat, an irreducible unitary representation of K prime of degree d sigma, you can construct the space of the representation as follows. So you take the set, the completion of the set of CD sigma valued function on SON, satisfying this covariance relation first, and this norm. And you have this inner scalar product to define the space of the representation, generic, let's say, generic representation. So if you have any sigma in K prime hat and any positive RQ, you define a representation by R sigma of M of n. So by this formula. And as you know, so this representation defines an irreducible and unitary representation of M of n, and we have the Plancherel formula for any f which belongs to L1 of M intersected by L2 of M of n by this formula. So the two norm of this function is nothing like this formula. So here you take the Hilbert-Smith norm as I explained earlier, and here there is some normalization of the Lebesgue measure on 0 infinity, and here you have the volume of this sphere. I think the colleague in Bangalore worked a lot on this kind of on this stuff of Plancherel formula and so on. So as a consequence, now if you change f, if you take any f in L1 intersected by L2 LP for M of n, then the Q norm of the F Fourier transform is given by this formula. So just you look at the Chatham class norm here, CQ to PQ, and you keep the normalization of the Plancherel normula. And as I said earlier, this is some mixture of a continuous spectrum and a discrete spectrum. So we have the following. For instance, the LP Fourier transform norm of the group M of n is EP to the n. And EP to the n is exactly the norm of Rn. And this says that the semi-direct product of S1 doesn't play any norm, any role in the computation of the LP Fourier transform norm at this level. And beta, we can show that this Gaussian exponential minus a squared over 2 is an extremal function at this level. And more is true. So this computation can be generalized to encompass all compact extension of Rn, not necessarily S1 or On, the orthogonal group, but you take any semi-direct product K with Rn, and K designates a compact subgroup of the automorphism group of Rn. Then we showed that for any p between 1 and 2, that we have this formula. So the LP Fourier transform norm of the group is given by EP to the n. And now you can even go through the universal covering of EM of n. This is called the spin n semi-direct product with Rn, and spin n designates the universal covering groups of the orthogonal groups. Here, the action of spin n on Rn is merely the pullback of the action of S1 on Rn. So just you look at the same action and you take the universal covering of the orthogonal group to designate this by spin n. For instance, it is well known in the literature then for n larger than 3, spin n contains a central 2 elements group Z2, such that the quotient is S1. So it is nearly something like similar to compact group. So even in the proof of this result, it is not a big thing with respect to what we have showed for the compact case. But for n equal to, the spin 2 is R. And we end up with the M2 tilde, so universal covering of M2. So it is a spin 2 semi-direct with R2. And we end up with a solvable non-exponential Lie groups with a trivial center. And here, still, we have a lot of difficulties to compute the exact norm of the LP Fourier transform on this group. For trivial, for evident case, just some similar difficulties as we meet in the three-dimensional Heisenberg group. So here, for instance, the group R acts on R2 by theta xy. So it is x cos. So it is, let's say, R acting on R2 by rotation for xy theta in R. And a long computation shows that the LP Fourier transform norm of M2 of tilde is dominated by EP squared. So we get therefore that if you fix any semi-direct product spin n on Rn, semi-direct product Rn, then for P between 1 and 2, so you have that the LP Fourier transform norm of G is EP to the n whenever n is larger than 3, because spin n divided by the two element group is S1. And for n equal to, we have only domination. We don't have equality. So the equality holds only in the case where n is larger than 3. And now let me move recently to some new results which generalize in some sense all these results. So we try to tackle the compact extension of locally compact group, trying to get estimate of the LP Fourier transform on these groups. So so this is the situation of unimodular locally compact group of type 1, and we can provide the generalization of ratio results for compact extension given for some specific P in such a way that Q is an even integer. I will explain exactly about all these new results. So we prove the following. Actually, if you have a separable unimodular locally compact group general of type 1, and you fix a closed normal subgroup of J, and you suppose that N is unimodular and type 1, and you assume that G mod N is compact, then in this case, the LP Fourier transform norm of the group J is dominated by the LP Fourier transform norm of N. So this generalizes the result of section 2, stating that spin N semi-direct of Rn or SON semi-direct of Rn, any compact extension of Rn. So here we assume that G mod N is compact. So this is the first new result. And now it is possible to treat the case where G is a separable unimodular locally compact group of type 1 of the form GK semi-direct product of N. So N here is a separable unimodular locally compact group of type 1, and the K stands for a compact subgroup of the automorphism group of N. So it is equipped with the group law of semi-direct, defining the semi-direct product of K and N. So we shall provide now sufficient condition under which the equality holds in 1, 1. And it is a generalization of theorem 3, 3- and 4. So this generalizes all these results. So let me remind what is 1, 1. 1, 1 is that. So this says that the LP Fourier transform norm of the group J is all the time dominated by the LP Fourier transform norm of N. But there is no equality. I will give later on some counterexample. So, the upshot is the following. So if you take any semi-direct product K with N of separable unimodular locally compact group of type 1 and the compact subgroup K of the automorphism group of N, then for P between 1 and 2, we have all the time equality. Fp of G equal Fp of N, if in addition the group N has a K-invariant sequence function phi G in L1 N of N anteceded by LP of N, such that we have some sequence tending to the norm. So we couldn't prove these results if the sequence is not K-invariant, and this is a bigger problem. So whenever you have a K-invariant sequence of function sitting in L1 of N intersected by LP of N, such that this goes to LP of N, and in this case we have equality. Otherwise, we don't have a counterexample, but we couldn't run the proof. So still the proof is not easy at this level. So, but in general, we may have that the Fp of G is different from Fp of N, not in the semi-direct product, but in this setting. In the setting where G is separable and you have a subgroup which is unimodular at type 1 and G mod N is compact. And this situation is, for instance, the situation where G, the group J is R and N is Z. So then G mod N is the torus group T and R is the compact extension of Z. So in this case, you have the Hausdorff Theorem inequality of Fourier series telling us that the LP Fourier transform of Z with the dual Z hat, which is isomorphic to the torus, and the Fourier transform is given by this formula. And this is actually classical and well known. And we have Fp of Z equal 1 because if you take any function on Z defined by this formula, so f of 0 equal 1 here, and f of m is 0 for m different from 0, then obviously fp equal 1, and the Fourier transform of the function f q equal 1. There, for any p between 1 and 2, you have that the LP Fourier transform norm of R is EP, as in Beckner results. I showed that in the first slides, which is strictly smaller than FP of Z, which is equal. So this is actually a counterexample, but it is not a counterexample for the semi-direct product. In the situation of the semi-direct product. And so as I said, so this example shows that G mod n is R mod Z acting trivially on n equals Z by conjugation. And thus the experimental function f of for f is invariant. Nevertheless, the equality does not hold. Now, also Rasso in 78 obtained the inequality that fp of G mod k is dominated by fp of J for any p between 1 and 2 in the situation where J is a unimodular locally compact group of type 1 and K is a compact normal subgroup of J. So it is normal and compact, then we have this inequality, and this holds for any p. But in the case, when you look at the case of a direct product of K, direct product with N, so you have the LP Fourier transform norm of the group N is dominated by FP of J using this result. Using this result for any P. And now for using the other result of Yusu, showing that when Q is an even integer, you have the another inequality. So if you combine these two results, you end up with this equality, saying that the LP Fourier transform norm of the group J is exactly the LP Fourier transform of the group N, but you assume here that Q is an even integer. Is an even integer. Otherwise, you cannot get a proof of these results once you remove this condition. But if you use the theorem 6, I just told you about our results with the Junko anyway. So if you fix any G of the form K direct product with N of separable unimodular locally compact group N of type 1 and the compact subgroup K, then in this case, the group K acts trivially on N by conjugation. So the action is trivial. Then the sequence, you have a sequence which is K-invariant because the action is trivial. And then using theorem 6, you have exactly this equality at this level. So the LP Fourier transform norm of K semi-direct product N equal to FP N without using these arguments of Rasso. And here there is a restriction that Q should be integer, an even integer, but here you have for any P between 1 and 2, you get this result. So finally, remark also that Rasso also proved that, so he obtained the inequality that when you look at the direct product of R with any unimodular locally compact group H, and you take any P between 1 and 2, then you have this domination. So actually, the LP Fourier transform norm of the direct product R with H is dominated by EP to the FP of H. And for the case where H is a compact group, so this inequality concerning the direct product GK gives the equality. And you have this, so FP key times direct product with R is EP. And this is nothing but FP of R, which is given by Beckner result for any P between and 2. And this is also a direct consequence from theorem 6. So this is the generation of Rasso result giving this inequality. So it becomes actually an equality whenever the group is compact. Thank you so much for your listening, and thank you all, once again for this invitation.
Thank you very much for an interesting talk. Now, I think, are there any questions or comments?
Yes, I have 2 questions. Hello, hi. Thank you for the nice talk. First one is, so you talked about the motion group. Do you know what happens if we just look at the rotation group? So what I'm asking, let's just talk about the unit circle in R2. Do you know the norm of the Fourier transform for S1, the unit circle in R2?
Yes, it is 1. For any compactly group, the norm is 1.
And the extremizers exist, and we know the extremizers are.
Sorry?
And do you know the explicit extremizers or the maximizers?
Yes. I have already I have already showed that for any compact group, the function f equal 1 is an extremal function.
Oh, the constant functions. Okay.
Yeah. The constant function is an extremal function. Yes.
Okay. The second thing is, if I remember correctly, the proof of Beckner was like some sort of discrete approximation to the set of Gaussians. And can you please talk about a little bit, maybe 1 line or 2 about the difference or the difficulty in proving the same kind of result for motion groups? Like, So how? So just a line or 2 maybe about the idea of the proof for the motion group.
Yeah. So this is actually a big problem because, for instance, if you look at the situation of Heisenberg group, there is no extremal function. You can show that the norm. So I showed that in some slides. So the norm is given by EP to the dimension 2n plus 1. But in this proof, any extremal function is shown to be 0. There is no an extremal function. What we say that what we show that there exists somehow a sequence of function in LP of J anteceded by LP which tends to the norm. So there is complete absence of extremal function in many settings, starting from Heisenberg group, for instance. And in the Euclidean motion group, it's easier because we showed that the Gaussian function are extremal function.
For motion groups.
For motion groups, yeah. Not only for motion group, any compact extension of Rn. Any compact extension of Rn.
Thank you. And can I just last one? Thank you very much.
Yes.
Can I please, for a few seconds, look at the singular integral thing you had on one of the pages, Calderon-Zygmunt singular integrals. I think maybe page 9 or 10, maybe.
Can you repeat, please? I didn't understand the question, please.
The singular, you had you were saying something about the singular integrals, about Calderon-Zygmunt singular integrals operators. About some sort of.
I think he means the Hausdorff operator inequality.
Yeah.
Source result.
Naru, can you explain? I didn't hear very good. So
it is the Hausdorff inequality for the operator valued integral operators.
Sure. Yes.
I think he wants to see that.
Yeah. Thank you. Yes.
So this is very general things. So they applied that to show that the Kunze theorem. So it showed that for any locally compact unimodular and type 1 group, so the LP Fourier transform of any group is dominated by 1. And Fourier and Rousseau developed this theory, and they gave this domination through general operators, and it is very helpful and very useful for when we treat some problem like that for general groups.
Okay, thank you very much.
Can I ask a question?
Yeah, sure.
Yeah. So when I look at your theorems 5 and 6,
yes,
can be generalized to a class of groups called sin groups. Do you know sin groups?
Sin groups, I heard about that, but for the moment,
it is.
So
if you quotient out the center, then it is compact.
Yes.
And if you assume that it is connected, then it is given by semi-direct product of a Euclidean group and a compact group.
Yes.
But if it is not connected, then it may give some complications.
Okay.
And I somehow feel that these things can be carried over to the. They are also called ICC groups, you know.
Yeah. I think so. In our theorem, when we look, for instance, for the compact extension of Rn, we didn't assume that K is compact.
Okay.
So, K is general. Even K could be finite. It could be finite.
But the inequality, you can improve the theorems, no? When you go for K to be compact. Can you think of having extremal functions for sin group?
Yes. So let make it precise. So if you take compactly group,
yeah.
So you have all the time the LP Fourier transform norm is 1.
Yes.
And you can adjust some normalization in a way that f equal 1 is the external function. So this is no problem. It doesn't depend on the connectedness of the group. But what is more important is, for instance, when you look at, for instance, nilpotently group,
right.
You cannot, so far, you cannot remove the connectedness. You can remove the simply connectedness, but not the connectedness. This becomes very complicated.
I see. Yeah, okay. Yeah, okay. Thank you.
Okay.
Are there any more questions?
Yeah,
I just thought of asking, can these results can it go through the inverse limit of groups?
Yes, in principle, yes, but I didn't look at that. But let me say that even for semi-simple groups,
yes,
nothing is not so far.
Yeah. Thank you. Thank you.
Yeah, for instance, in SL2 or in SLN.
Yes.
I have been informed that Japanese students is starting to look at that, but nothing in the literature. So this problem basically concerns right now some solvable and the compact extension of solvable for the moment. Yeah.
Okay. And for the motion group, all these irreducible representations come as spherical representations. Yes. No?
Yes. Maybe yes. Yes.
Yeah. So maybe because your compact group is operating or something, we can give a better result when we consider only spherical representations.
Anyway, we need the Plancherel measure and the Plancherel formula. Maybe for some groups which are not only compact, but some compact, some direct product or something like that, maybe we need that. But if you like to compute the norm, the exact norm, maybe spherical representation are not enough.
Okay.
Yeah, so I was wondering, in the case of any of these non-compact group,
yes,
if one can go a little bit beyond the 2, here all this now P usually is restricted between 1 and 2, just like in Rn. So, but in the case of non-compact groups now, is it possible to go a little bit beyond? I mean, with some kind of, say, some very nice representation for some group which has a nice, is it possible?
Sorry, Pradeep, I didn't understand the question. So you speak about the spin group, the semi-directive spin group, right?
No, I was wondering, this usually this Hausdorff inequality, say for instance Rn, we split between 1 and 2, right? And beyond 2, if you go, you end up in general in some tempered distribution. That is what I know. But so in this context, I was wondering, in the case of groups, if you take a non-compact group, is it possible to go beyond 2 so that some estimate effect makes sense in a reasonable way? I mean, because here you are, I'm not even restricting any group, so the representation is good enough so that you may get something. So I am wondering if any such thing is, you have some idea that is.
Yeah, in general, the knowledge of the representation is very important in this problem. So maybe I didn't hear very well. Naru, can you explain what is the kind of group Pratip is speaking about?
No, I think he is asking for results for p greater than 2.
Yeah. P greater than.
So maybe for compact groups one can.
Compact, yes.
One can ask, but non-compact perhaps you cannot even ask.
Okay. This is not a very big issue, because when p is larger than 2, the conjugate of p is between 1 and 2.
Therefore,
the conjugate becomes between 1 and 2. So it is not. So this problem is dual.
It will be the same. That is, the answer will be the same.
It will be the same.
So if you know there is a Hausdorff inequality, but then the Hausdorff inequality holds only for p bigger than 2, don't know where it is.
Does it apply to Rn then?
No, it doesn't apply, because if you take the Fourier transform of an LP function with bigger than 2, then you end up with a tempered distribution. Not for every. You don't get.
So here, how does the duality apply then? That is a question.
Yes. If you, for instance, if you take p larger than 2 and your q is between 1 and 2, and you take the problem in the dual form. So in this case, the problems in general settings, it comes to itself. So I think it's not a big issue. I'm not quite sure about when you look at.
No, I'm not convinced.
Rn is fine because the Fourier transform is the symmetric setup.
Yeah. For instance, in Rn,
you can't even make sense out of that, right?
No, Rn also, it is. I mean, there if you try to do, you end up in the tempered distribution, no?
No, but you have to restrict to tempered distribution whose Fourier transform is seen in LP.
Yeah.
In the dual.
Then I was actually asking this because here you have freedom to take representation. So some kind of group where it may.
First of all, you need an inequality to improve. You need an inequality to talk about the short constant, right? If you don't have an inequality, then there is no question of finding the short constant.
Yeah, no, I was trying to see if it can be made sense, at least for some groups. In the when you play with the non-abelian situation, no, there may be a possibility that is asking. Yeah,
but
just
in the case of R and LP, LQ, then Q has to be the dual, right?
Yeah, the dual, yes, exactly, yes.
Yeah.
There is no other way.
Yeah,
that is true. Yeah.
But in the case of other groups, you cannot use this kind of a dilation argument to prove there is no such things.
Yeah.
I don't know whether.
True, yeah. So I have a feeling maybe some group, things are better. So it may be possible because if you have a nice representation, I mean that there may be a possibility that is curious to know. Because there may be new things in different context.
Okay, yeah, then the problem is to find such groups, existence of such groups first.
Right. Yeah.
Okay, thank you.
Okay. Thanks for the nice talk.
Yeah, thank you very much.
Yeah.
Just off and I think let's